We have reached the heart of the drone, its engine. The propulsion system is what gives the drone's life, determining its speed, power, endurance, and ultimately its entire mission capacity. The choice of how to power a drone is one of the most fundamental decisions of engineers make, and it is not one size fit for all solution. All the slides layoff to the world of drone propulsion is divided into two major camps: the quiet efficiency of electric motor and the raw power of chemical engines. The choice between the two opposition philosophy entirely depends on the operational requirement of the aircraft. Let's first talk about the system that has powered the drone revolution and is familiar to most of us, the electric motor. This is the propulsion method of choice for vast measure of small and lightweight UAV, from the tiny nano drones that can lift in the palm of your hand to the sophisticated quadcopter used for film making and harvest. The advantage of electric motors are numerous and significant. They are incredibly efficient and converting electrical into rotational force. They are remarkably quiet, which is a huge benefit for applications like wildlife monitoring or security. And they are relatively simpler and lightweight. These motors are almost exclusively powered by lithium polymer or LiPo batteries, which offers the best energy density currently available in lightweight packages. This combination of light motor and light power source is what makes the agile, compact design for multi-rotor drone possible. However, the world of electric propulsion is covered by critical trade-offs. While the light and efficiency, they are fundamentally lower in power output compared to the chemical engine. The energy density of each best practices farms in comparison to that of the liquid fuel. This is the primary reason for the limited flight times and the range of most electric drones. They offer precision, quietness, and simplicity, but at a cost of raw power and endurance. Now, let's shift the gear to other side of the spectrum, the chemical engine. This is the realm of heavy duty, high performance drone. When a mission requires carrying a heavy, a very heavy payload or staying in air for an extremely longer period, the limitation of battery power comes insurmounted, and the engineers turn to the brutal force of combustion. These systems are typically small gasoline engine, just like you might find in a Lamont or a small motorcycle, or in most powerful jet engines for high-speed military application. The single greatest advantage of power which is given by chemical engine is incredibly energy density of the fuel. A small tank of gasoline contains vastly more energy than the battery of the same weight, which is why fuel-powered drone can have a flight time which is measured in hours, not just in minutes. This makes them the only choice for large UAV design for extensive surveillance, a large heavy cargo uh, transportation, a long range aerial agriculture surveillance or military surveillance. However, this power comes at a cost. The chemical engine are significantly heavier, more mechanical complex and louder, and they also produce vibration and exhaust. They are not suitable for small agile drones. As the size indicated, the combustion engine itself will almost occupy a medium size a drone, while the most powerful turbojets are reserved for larger, heavy military platform that demands for higher speed and performance. Ultimately, the choice is clear. For agile, precise stealth, and in small packaging, electric motors are good. But in terms of raw power, heavy lifting, and marathon endurance, the proven technology is to be a chemical engine, and it remains to be the supreme leader among the two. We just discussed the engine that drives our drone, but the engine is useless without fuel. We now arrive at what arguably the single most critical component to determine a drone's real world performance, its power source. The power source is the lifeblood of a drone. It dictates how long it can fly, how much it can carry, and ultimately what mission it can accomplish. The undergoing development in this area, particularly in battery technology, is constantly push and pull between incredible potential and significant challenges. Let's explore the primary power source used today and a critical endurance challenge that presents. The undisputed king of consumer and prosumer drone world is the lithium polymer or the LiPo battery. You can see it listed as one of the battery technology alongside lithium ion and nickel metal hydride batteries. Lithium battery rose to dominance for two simple reasons. They have high energy density, meanwhile they pack a lot of power into small spaces, and they have very lightweight design. This high power to weight ratio was essentially ingredient that enables the multi-rotor revolution, providing enough power to these agile drone off the ground without weighting them down excessively. Virtually every drone you see for photography, inspection, or recreation is powered by litho batteries only. However, for all these benefits, lipo batteries are also the source of the drone industry, the greatest endurance challenge. The stark reality is the most battery-powered drone have a flight time of only 20 to 30 minutes. This is the biggest bottleneck holding back their practical application. An interesting and often overlooked factor is that this already this already short battery life actually decreases its altitude. This happens for two reasons. The air gets cooled when cooled down its chemical reaction inside the battery, reducing its efficiency. And the air gets thinner, which means the propeller have to spin faster to generate uh, same amount of lift, draw more current from the battery. Because of these severe limitations, improved battery power density remains the core focus of the future drone development. This is the holy grail of drone research and development. To overcome the limitation of battery, engineers have turned to other power sources for more demanding mission, which we touched on the fuel system before, and they represents the current solution for heavy lifting and long endurance. Typically, in large drone, a small gasoline engine provides far most power for carrying larger loads and keep on aircraft in the air for many hours. They offer a massive leap in capability, but they comes with a logical requirement of storing, handling, and refueling liquid fuel. Looking towards more sustainable and high-tech future, we have solar power. Solar power integrated into the drone's wing often offers a clean renewable energy source for most drones. Solar isn't meant to be the primary power source, but rather a way to extend the mission. It acts like a trickling charge for onboard battery, significantly stretches the operation time. This technology is primarily used in highly specialized long endurance fixed wing drones designed for scientific and military missions. Some of some of which are engineered to stay aloft for days or even weeks at time, harvesting the sun's energy during the day to power their flight and charge their battery for flying through the night. In the end, the power landscape is clear. If a battery drives the mainstream market are limited to endurance, fuel system provides the brute force needed for heavy work at long range, while solar represents the cutting edge of extreme long-term endurance. The future of the drones are achieved uh, is are linked to the next breakthrough in how we are going to power. We have just covered the various power sources that act as the fuel tank for our drone. Now we are going to look at the component that actually converts the power into the force for flight, starting with arguably the most critical component of multi-rotor propulsion system, the propeller. It is easy to uh, dismiss them as a simple spinning plastic blade, but in reality, propellers are sophisticated, carefully designed airfoils. They are drawn swing. It it is a rudder and its engine rollout and its engine are rolled out and their design and configuration are absolutely critical for everything the drone does, from lifting from the ground and to execute a precise maneuver. The propellers have three primary functionality. The most obvious job is to generate uplift, just like a airplane wing. The propeller blade is in aerofoil shape. As it spins, it shapes to pushes the air downwards, and according to Newton's third law, it creates an equation like equal and opposite upward forces that lifts the drone and counteracts the pull of gravity. Secondly, the drones are capable of precise maneuvering. As we have discussed, we uh, we have to make precise movement. By precisely varying the speed of individual propeller, the flight control makes the drone do motions like roll, pitch, and yeah, allowing it to move in any direction. They are the drone um, are the drone's only control surface. Finally, they are responsible for maintaining stability. The drone's flight control is constantly making thousands of micro adjustments to the speed of each propeller to counteract the wind and turbulence, keeping the drone stable and level during the flight. Now, how to make all of this work, we have to solve the fundamental physical problem, torque. All of the propellers of a quadcopter spun in the same direction. The rotation force would cause the drone to spin widely in opposite direction. The solution is elegant quadcopter configuration, as you see along in the slide. The propeller are installed in the parts, two clockwise propellers and two counterclockwise propellers. They are arranged diagonally in opposite to each other. For example, the front and rear motor spin in the clockwise uh, the while the other two rotate in a counterclockwise direction. This arrangement perfectly cancels out the rotational torque force during the stable hover, preventing the drone from spinning and providing a stable platform. This performance of this propeller is determined by several key factors. But we'll focus on two of the most important thing: the pitch and the diameter of the propeller. The pitch can be thought of as aggressive of propeller's blade angle. By a simple visualization, we can think it of propeller as a screw moving through a wood. The pitch is the distance the propeller would move forward when one revolution happens. The higher the pitch means the blade might move into more air while it is making the rotation, which generates more lift and thrust. However, it comes at the cost of higher power consumption. The diameter is simply the length of the propeller from the tip to tip. The larger diameter propeller moves the larger volume of air, which can generate thrust more efficiently and at a lower RPM. The slide notes that the larger diameter affects the uh, rotational inertia and can lead to more stability. This is because the larger spin acts like a gyroscope, helping it to smooth out the drone's movement through it makes slightly responsive to rapid turn. As you imagine, and as you see the key insights of the slide points out, there is no single best propeller. The design of the drone propulsion system is delicately balanced. An engineer must carefully select the pitch, diameter, material, and the shape of the propeller to achieve the desired performance of specific mission. A drone built for high-speed racing will have a very different propeller than the drone designed for heavy lifting cinematography. This is carefully combination of balancing these factors that results in stable, efficient, and high performance aircraft. We have just examined the propellers, the components that bite into the air to create thrust. But what makes these propellers spin? And how does the drone's brain tell them how fast it has to spin to make microscopic precision adjustment? To understand that, we must look deeper into the engine room of the drone at the critical component of the propulsion system. The slide introduces the muscle, the nervous system, and the circulatory system that works in the perfect harmony to power and control the aircraft flight. The muscle of the operator is the brushless motor. These are workhorses attached to each arm of the drone, and they are technological marvel in their own right. As the slide gets into deeper, the several key characteristics that makes them ideal for the jobs are shown. They offer a high torque output, which means measure their twisting forces. The high torque allows them to change speed of the propeller most instantaneously, which is the key to drones' incredible responsiveness and stability. They are also highly efficient, converts more of the battery's electrical energy into rotational force with less wastage of heat. And finally, their low noise operation and lightweight design are perfect for creating the compact, relevant, quiet aircraft we are all familiar with. Now, a motor on its own doesn't know how to spin fast. It needs a dedicated brain to give its command. This is the role of electronic speed controller, or the ECS. You can think of ECS as a central nervous system for each motor. This is the small circuit board that sits between the drone's main flight control system and the motor itself. Its primary job is to take the high-level command from the flight controller, like spin at 70% power, and translate them to the series of precise electrical pulses that tells the motor exactly what to do. The ECS are what regulates the motor power and allows the drone to change its speed. Every time a drone accelerates, stop, or makes a turn, it is a result of ECS flawless execution command to achieve precise control. They also incorporate important safety features like shutting down if the motor is drawing too much of current while helping them to prevent catastrophic failure in the air. All of the uh, all of the all of these components needs a reliable source of electricity, which brings us to the power distribution system. If the motors are the muscle and the ECS are the nervous system, then the power distribution board or the PDB is the heart and the circulatory system. It takes the main power from the single drone battery and safely distributes it to each of the ECS. But it does not. But it does more than just splitting power. A good PDB also manages the power flows, often containing protective devices like flicks or fuses or voltage regulator to ensure that clean, stable power is delivered to all the sensitive electronics. This provides an element of a fault tolerance, helping to isolate a problem in one part of the system so it doesn't take down the entire aircraft. Finally, we have the various supporting elements. They are unsung heroes of the propulsion system, the small but critical part that ensure everything works reliable. This includes the durable motor casing that protects the dedicated material uh, like high quality winding bearing and that allows the motor to spin smoothly for thousands of hours and cooling system like heat sinks that provides the motor and ECS from overheating during high performance flight. As the slide's key insight states, none of these components work in isolated. They are all of a part of single tight and integrated system. This makes seamlessly cooperation between these parts that provides efficient, powerful, and exceptionally precise propulsion that defines modern drone technology. We have explored the different ways drone are built and how they fly, from the efficient fixed wing to the agile multi-rotor. But the other, a more fundamental way, we categorize these aircraft by size. It might seem simple, but classifying drones based on their physical dimension and weight is a critical important category. Size isn't just about how big a drone it is. It is directly dictates its capability, its power requirement, its payload capacity, and uh, crucially, the regulation that governs where and how it can be flown. As we go through these classification, from the tiniest nano drones to the massive military platform, you will see that the word drone covers astonishing vast range of technology. Let's start with the small end of the spectrum with the nano drones. Sometimes it is called as the nano aerial vehicle or NAV. These are truly tiny vision. We we are talking about a maximum size of 7.5 centimeter and weights around 250 grams. To put that in perspective, they can easily fit into your palm of your hand. Their small size makes them incredibly difficult to see and hear, opening up with a unique set of applications. The slide mentions the precise task and insect size monitoring. This is the realm of espionage and a close quarter inspection. Uh, the imaging a drone can fly through a small cracks in a wall to inspect a damaged structure from inside, or one that can act as a almost invisible observer for security and wildlife research without disturbing the environment. Their light weight is also a key regulatory threshold for many countries, often placing them as the safest category with the fewest restriction. Moving up, we have the microdrones, or a micro aerial vehicle (MAV). Their size ranges from 7.5 to 15 centimeter and weighs up to 250 grams to 2 kg. This category that most people are familiar with. This is the sweet spot of vast consumer drone market. The popular foldable drone used for photography, videography falls into this category. They are large enough to carry a high quality camera and they have decent flight time, but still small and light enough for easy portability and reliably safe for operating. The application listed like consumer photography, light mapping, and perfectly captures their road. They are go-to tool for the hobbyist content creator, professional who need capable aerial camera without moving into heavy grade industrial equipments. Next, we enter the realm of small drones. With the size of 15 to 20 centimeter and weight of 2 to 25 kg, we now firmly into professional grade category. A 25 kg drone is a serious piece of equipment that requires skill and certification to operate safely. These drones are workhorse. The application are aerial photography and basic mapping might sound similar to microclass, but the capability are step above. We are talking about a drone that can carry heavy and more sophisticated sensor packages such as high resolution camera for professional surveillance or multiple sensor for more detailed depth mapping tasks. The 25 kg mark is the another way a very important regulatory boundary in the most part of the world, often separating the standard commercial uh, operating from the advanced heavily regulated one. Here we take a significant step in scale to the medium drone, which size they can range from 20 centimeter up to 10 meter and a weight of 20 kg all the way up to 150 kg. They are a long tool can carry in their backpack. They are large industrial mission. Their application reflects their scale. Advanced mapping doesn't mean taking picture. It means carrying heavy LiDAR system to create incredible detailed 3D models of terrains or infrastructure. Agricultural monitoring at their scale isn't a small feat. This is for surveilling a vast commercial farm, requiring larger flight time and a heavy multispectral sensor payload that these airframe can support. They are sophisticated tool for big data intense job. Finally, we arrive at the top tier, the large drone. With a size greater than 10 meter and weighs over 150 kg, these drones are often on par with the small uh, manned airplanes itself. As the application clearly states, this is the domain of military operation and a long distance transportation. These are advanced surveillance platform that can stay on airborne days days at time. Your large scale cargo drone designed to move heavy goods between logistic hub and your high speed tactical aircraft. These represents the pinnacle of drone technology in terms of size, capacity, and cost. The logarithmic scale on the drone doesn't give a greater job of the visualization. Their incredible range. When you see the tiny silver representing nano drones next to a massive bar of large drone, it has truly underscored that an insect-size spy to an intercontinental transport. The world of drone technology is widely most diverse than most people can ever imagine.